Okay, welcome back. More latent growth curve modeling talk, or growth curve modeling, or latent growth modeling, whatever you want to call it. So today I'm going to go over some examples from some data. I'm primarily going to use categorical variables that are ordinal, in some cases binary. It's interesting though that I'm actually reviewing a paper written by somebody for a journal that discusses issues when you're doing binary versus ordinal variables and why we shouldn't assume that binary variables are a special case of ordinal variables. So, got to keep that in mind as I'm reading this. And the person makes a really good argument, and I'm just going through the review process right now as a reviewer. So, but I'm going to just go with what I've done in the past, okay, at this moment. So, what I thought it would be best to do would be to just run a few different kind of growth curve models. Again, all of these ones are using either ordinal or binary variables. Okay, so these are some examples from previous research that I did with some colleagues. And this is an example of electronic cigarette use. So in this case, we had electronic cigarettes being some kind of a categorical variable that we created. Usually we would have created categorical variables that are either did use and didn't use, or it could be an ordinal variable that had different levels of use. So in this case, I'm just going to run a simple growth curve model. And so I'm going to also do some changes to this model as I go on. So let's take a look at this coding here. So I have my location of my data. I have my variable name. So in this case, I had a lot of variables. And the way missing data were defined as 9999. So any case that has 9999 in it is considered missing. The variables I'm using in this analysis are these e-cigarette, electronic cigarette use variables across these different time points, 5 time points. Of course, I define them as categorical. That's the necessity. All dependent variables have to be defined if they're categorical as categorical. I'm not defining them as binary or ordinal, I'm just defining them as discrete categorical. And then I go ahead and go ahead and create my model. So I don't have an analysis command yet. I will in a moment as I make some changes here. So I define this model as being linear with its intercept and slope. I don't have any curves yet. I'm just doing a straight line. And in this case, I have it modeled as a line. So these are my fixed factor loadings, right? So I fixed them to equal 0, 1, 2, 3, and 4, since I have 5 different time points that are equally spaced apart. So I can just make a line as 0, 1, 2, 3, and 4. And I also look for modification indices, but I can't remember at this point this was a while back when I did this, whether I used that or not, but we have them in there anyway, just to help us take a look at if there's any issues with the model. Okay, so I'll go ahead and run this model. And again, this is using comma separated variables. All right, in this first run, it shows that I have 1,840 different values. Or warning, the input line exceeds 90 characters. Some input may be truncated. So I think that's this line right here. So it likes it to be less than 90 characters, apparently. 90 characters or less. This shows you the type of estimation, that method that's being used. Also, parameterization, delta method parameterization. Okay, here are my distribution of my categorical, or in this case, binary variables across time. Right? Just there weren't a lot of people vaping early, and you get up to 11% later, right? But started lower, like 6%, and then went to 11%. Here I have my model fit statistics. So this is the chi-square test for model fit. It is significant, meaning that there's some misfit somewhere. And my other my other, like the RMSEA, the CFI, these look okay. They look okay, but we could see if we can improve this model some more. Ideally, it wouldn't be, you'd like this to be non-significant. Let's take a look at my modification indices, see what they say here. So there's things that I could, you see, one thing, like you get these abilities to make certain changes, like, well, maybe I should freely estimate the relation between the intercept and e-cigarettes at time point 3, but I'm not going to do that because that fundamentally alters the model. One thing you don't want to do, I mean, if you have to do modifications, you're going to do something usually with the the like the error variances or something like that, rather than with some fundamental part of the model. And here it also tells us means are or thresholds are an issue. I think this is the indicator for means, right? So yeah, there are things that we could change here, but I'm not going to touch any of these ones. I don't agree with making these types of changes. But what I could do is I could test and see if I change it from a linear to, say, a quadratic model, would that do anything? So let's add a quadratic term here. So I'm going to add a quadratic term. I'm going to put a little q in here for quadratic. Again, it doesn't really matter what it is. It just knows that it's a third one, and that's the quadratic, right? Fourth would be the cubic. And let's go ahead and run this again. Ask me to save. Let's see if there's any changes here. As I remember there is, and then, look at here, we got some interesting information here. Okay, warning, warning, the residual covariance matrix theta is not positive definite, so it can't be inverted. This could indicate a negative variance, residual variance, for an observed variable, a correlation greater than or equal to 1 between the two observed variables, or a linear dependency among more than two observed variables. Check the results section for more information. Problem involving the variable e sig 3. The standard errors of the model parameter estimates could not be computed. The model may not be identified. So you don't want to use this. Now, this is like bad in a sense, right? So if I proceed this way, I might get results that are not correct, and I'm not going to do that. So I'd like to figure out what the problem is here. And this is what I want to look at, right? I want to look at the variance for e-sig 3, right? So what's going on, but I can't see them using things as they are now, the parameterization, this delta. So I have to switch to a theta parameterization, and that'll allow me, when I'm dealing with categorical outcome variables, to take a look at this and then do some modification if I need that. So I'm going to go ahead and add an analysis command, analysis parameterization equals theta. I spelled that right. We'll see. I think that I did. So changing this will actually allow me to look at so I still have the same error here, right? Involving variable e-sig 3. So let's take a look at that. What's going on? By the way, this fits nice, but let's take a look at what's going on with this. So, I mean, even though it fits nice, I still have a problem here, so I can't trust this model. So let's go ahead and see what's going on. Aha, look at this. So my residual, so as you know from the calculation of variance, right? Just think about variance, how it's calculated. You're squaring the difference between the value and the mean. So how could you have a negative variance? You cannot have a negative variance. So I think this is what's called a Haywood case. So it's a negative variance. And when that occurs, it's obviously indicating there's something wrong somewhere, because how could you have a negative variance? So a solution is to constrain this variance to 0. However, you only do that if we have a non-significant variance. And here's my p-value for that variance. It's 0.390. So I can do that. If it wasn't the case, I'd have to keep on looking, because you cannot do that. I mean, well, you can, but what's going to happen is you're just going to reduce your model's fit into the data. It's going to get worse. Constraining something that's significant to be something like 0 doesn't work, right? But here I can. So I'm going to go ahead and constrain this. So let me just go E sig 3, and I'm going to set that as so. This is my way to just say that I'm dealing with the variance. I'm not putting any brackets around it or anything like that. I'm constraining it with an at sign to equal 0. All right, let's see what goes on, what happens next. This could be fun. Run it again. Oh, so far, oh no, something else. What does it say now? E sig 4. Oh my gosh. So we have the E sig 4 is also a problem. So again, let's go and check out the variances. I go straight to the variances. There you go. It's also, well, it says it's residual variance is 0. Um, it's interesting, but you know what? Let's just constrain this one to equal 0 as well. It's not significant, so it's not going to hurt anything. Let's just do that. E sig 4 at 0. Right, save that and run it and see what happens. All right, so what's going on here? Worked fine. There's no more problems with the model with really nice fit statistics. So this is a good fitting model, and we can see some of these issues. These are just correlations. We see that, these are just, you have like growth over time, then you have this bend over here, the quadratic term. I mean, we can start adding. I can start adding things to this model, right? I can add things to this model. So let's see, how about let's add another variable like smoking here. We think smoking would increase the likelihood of using an e-cigarette. Well, I have no idea what's going to happen here. Let's see. So I added this variable, cigarette smoking. I don't have to declare it as categorical because in this case, it's going to be a predictor variable. And my model will be ISQ on smoke. So I'm regressing each of these values here, these latent variables on smoking. So let's see if it works. What happens? All right, let's see, did it work? Oh, now we got this problem with Q. Problem involving Q. So let's see what. So this is the way it works, right? Some people would say you just put the quadratic variance at 0 anyway, but let's see. Well, it's not significant, but it's not negative either. So I'm not really sure what the problem is here, why that is an issue. It says here later could indicate a negative variable. We don't have one. Or residual, a correlation greater or equal to 1 between two latent variables. So let's see if there's a correlation greater than 1. Do I have correlations here? I don't in this one. I didn't really ask for sample statistics. I wonder if that'll give me the correlation SAM stat. I think that's the code as far as I remember. I guess it's not the code. Maybe SAMP stat. Maybe it's SAMP stat. SAMP stat. Yes, SAMP stat, not SAMP stats. That gives me this stuff, but I'm looking for the correlations among the matrices. Excuse me, the correlations among the latent variables. And I don't get that here. Oh, I'd have to remember what that code is. Actually, I do get, well, that's not true. I do get the correlation. What am I thinking about? I do get the correlations here. Sorry about that. These are the correlations among the latent variables. Not seeing anything here, but what's some, set Q at 0. See what happens. Actually, let's go there. Q, it wasn't significant anyway, so. Clearly, there's some interesting stuff going on here that we have to deal with. Well, that worked, but look what happened because now I set its variance at 0. The model doesn't fit very well, so that's not a good solution here. But you can see that there's always going to be issues that you have to deal with, right? And if you don't deal with them, you could have variety of problems. There's no guarantee that things will fit well. I'm just going to try one more thing here. Sometimes when you have one variance that you set up. Yeah, so there's some problems with this model, but you see that I can go through a bunch of processes to try to figure out what's wrong. Maybe I didn't even need the Q variable. Maybe I didn't even need that. Let's see. Back here. I mean, that was one of the things that I thought would work to make the model fit better, or just to make it a little bit better fit. But if I don't do that and I just maintain a linear model, let me see what happens. Yeah. So I end up not having a very good fit. So the question is, do I need that other that quadratic term? Apparently I do need it, but then it introduced some issues there. So you can see that this is a tough process. There's other things I could do. Perhaps I could use an ordinal variable, but if we looked at e-cigarette use in these data, you saw that there weren't a lot of people using e-cigarettes, right? So the problem is that this is going to be a very small set. This category has a very small number of individuals in it. So look at that relative to the total 104, out of whatever 18 something, 1836. So these are issues that you deal with in growth curve modeling especially when you're dealing with discrete variables. All right, so maybe that paper I'm looking at could have some more insight that can't wait to finish reviewing it. I'm going to do that right after this class. All right. So that was an example of a growth curve model, and I really wanted you to see what it means to have errors in the model. Okay. So let's look at a different type of model. Now, this is an example of an associated processes growth curve model. That means there's two processes, right? Two processes, and in this case, we're running a mediation model. So I'm going to get rid of this for a second here. Running a mediation analysis. So here we have two different variables, and let's keep this as this. Okay. So we have two separate repeated measures variables. One was whether or not one used e-cigarettes. So similar to what we had last time in the last model. And the second one involves reasons for using electronic cigarettes. And I think I was looking at this variable here, why do teens? So this was from the original study. Why do they use them? E-cigarettes are affordable. People in the media or other public figures use e-cigarettes. So there's just it's a measure to see, do these reasons impact why somebody would choose to smoke an electronic cigarette? So that's what we were looking at there. And then, so there's that variable, and then we have a we have and it was also we made it into an ordinal variable too, right? So it was an ordinal variable. So ordinal variable. It was ordinal. We'll see in a second. Again, I haven't seen these data in a long time. And then we have also electronic cigarette use. Okay. And let's see, there's a bunch of other variables in here, like that we want to control for gender, race. This was being African American versus not African American. This was dummy coded 1-0, Hispanic being Hispanic versus not Hispanic, other race. And I can't remember what sex was. Was it 1 female or 0 male? It's probably that. I'm not 100% sure. Smoking status at the first time point, peer household smoking. And smoking for harm reduction or uh, only changing to vaping for harm reduction and to reduce cigarette smoking, something like that, right? Again, I'm more interested in showing you the analysis here than anything. So let's look at this model. So this is an associated processes model. So there's two different processes here. So you have e-cigarette use at these different time points. And this is modeled as a linear growth curve, again, because we have them measured I think they were measured 6 months apart. So you have a unit of time is 6 months. So starting with baseline at 0, 1, 2, 3, 4, 5, 6. So there were a bunch of time points here, right? 7 different time points. This is a lot more, a lot longer. And the same for reason. We have the same thing. And just to avoid having, that error that our data set, our lines are too long, I split this into two, right? So that 0, 1, 2, 3, 4, 5, 6. Okay. And you'll notice that the factor loadings are always one less than the number of time points, because again, we have to start at 0. So our first point is set as our intercept. This is the loading. That means there's 0 relation between the growth factor and the actual value at time point 1, set as the intercept. So then here we introduced all of the predictors, right? So because these are all ordered, I could just say, well, we're going to go from sex through harm reduction, right? And then so I'm doing I E-sig to S reason. So I'm going I E-sig to S reason. So this goes in order as well for latent variables. So I can just do this some dash here to indicate that it includes everything in those latent variable realm. Then I can do specific effects like and this is S E-sig, that's the trend factor. Is that trend factor influenced by the baseline level variable for reasons to use E-sigs? And then is the reasons variable influenced by the baseline E-sig? That's kind of usually what you do, right? That's probably what most people do when they do these models. And you can also add, although sometimes it can cause problems when you start having too many pathways to estimate. But this is what we want to know, does the rate of change in reasons influence the rate of change in electronic cigarette use? So that the idea there is that, well, if your reasons change, it'll change whether or not you increase or decrease the rate of change in e-cigarette use. All right, and then I asked for standardized coefficients and sample statistics. I like the standardized coefficients because they allow us to draw figures and plot the standardized values, because those are nice and easy to interpret. And then I asked for an indirect effect from smoking. So the idea is the smoking, I think probably the hypothesis here was that progression in electronic cigarette use was influenced by cigarette smoking, but indirectly through the impact of the reasons for use. So this code here says that anything that goes between these two would be counted as an indirect path. So any way that smoking can influence this would be an indirect path. So it could influence it through baseline reasoning or through reasoning trend. It could go two different ways here. All right, so let's go ahead and run this model and see what comes up. All right, so here we have 1799 individuals. We lose some people who had missing data on all the X variables. Right. All right, same kind of, so we're not doing theta, we did the theta in the other one because we were trying to correct that error term. Okay, so this is the reasons where we created a 4-level variable here. And this shows the distribution across the 7 time points. And then for the electronic cigarettes, and this one it wasn't binary, we had a 4-level. So the binary stuff doesn't influence us here. So this shows us the distribution of all the dependent variables in the model, the variables that have the arrows pointing at them. That's what we're looking at here. The ones that have the arrows pointing at them. We get our threshold. I love having the thresholds. Thresholds, they link the observed variables to the latent variables. Like there's these propensities to increase or to smoke or to vape or to whatever it is. It gives us like propensities. And let's just go down to nitty-gritty. So this is model. You can see the fit is pretty, it's not very good, but this is going to happen when you have more complicated models, right? If it's not going to be as good, you just have to deal with that. I mean, you can, first thing, in the past, a lot of people did not report, and some critics were saying, well, you don't report the p-values. And that's really important in the chi-square value. You have to be transparent and say this model did not really fit that grade. I mean, that's a lot of misfit. And obviously I could do things to make it fit better. I could try to test different types of trends, but again, for this is just a video where I'm just going to talk to you about how this program is working, right? So I guess RMSEA value looks pretty good. They're pretty low. CFI is above 0.95. So in terms of this stuff, I mean, we're doing nicely. SRMR, it's really low. These are all really, really, they're nice, but you still have that chi-square test. That is significant, and that's always a problem. So make sure you acknowledge that. In terms of what we see here, we have positive effect of reasons for vaping influencing rate of change in vaping, which we expect both baseline and then rate of change in reason. So these are both would be positive results for a researcher who wants to show that. You also have baseline e-cigarette smoking influencing. So it's kind of which one comes first? That's kind of what we're looking at, which one comes first. So this is important to always, be very transparent on what's going on in terms of some of the impacts on baselines, e-cigarette use. You see a lot of them are significant. Again, this is a large data set too. So you get significant findings when the data sets are large because you have more power, right? Household, smoking, pure smoking. I think this is vaping or smoking, could be pure vaping, cigarette smoking. All of these have significant effects. And then for reasons, you have fewer things, but you still have plenty smoking and pure. Yeah, well, it makes sense because reduction and harm, you do it for reduction and harm. Those are separate variables, but they're related, obviously, to why you'd want to vape. Okay. And as usual, sometimes you have negative effects on trends because maybe you reach a ceiling with your effect at baseline, so where you can't keep on going up, right? And so you start having a little bit of a reduction. And what I'm looking at here then is these indirect effects. A lot of data stuff. Okay, here's the indirect effects. Wow, these are great. So I get an indirect effect from cigarette smoking into e-cigarette trend through 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 reasons, and it's negative. Okay, so that's interesting. Negative indirect effects. So it's reducing the rate of change. Maybe it's because or I'm not really sure why, but it could be something to do with they choose a cigarette smoke versus vape. I'm not really sure. You do have this other specific indirect. So this breaks things down into specific and an indirect effect, and then a total effect, right? A total indirect effect, a total effect, and a total indirect effect. The total indirect effect is negative, right? And that includes these components right here, 1, 2, 3. So it picked every possible indirect effect you could have. Like this one's interesting, smoking, I mean, through baseline e-cigarette use to, it's just like very complicated, right? So you have all these different paths here. I mean, if you look at baseline reasoning, you have a positive effect. So this could also be some kind of a ceiling type of effect here. So it's interesting, right? But here's the problem, though. This is an indirect effect based on just the regular standard errors, and the standard errors in indirect effects can be flawed, right? There's no guarantee that they're going to be normal. So if they're not normal, if they're skewed. So imagine if you have a right skewed standard error, and you think about these tests, like these statistical tests. I mean, like any kind of, like say, like a Z test, for instance, right? Where you have a Z test, if you think about it, it's this where you standardize everything, right? your denominator is a standard error. And if that variance, which is a component of the standard error, is skewed to the right, you have larger variances, that's going to increase the size of the denominator relative to the numerator, and it's going to decrease the total, right? So you have less power. On the other hand, if you have a left skewed variance, right, smaller variance, that's going to decrease the size of the denominator relative to the numerator. So you're going to get what, a larger test statistic value, and you're more prone to have a false positive result, type 1 error. So this doesn't fly. And if any good reviewer would say, well, but you didn't, you didn't, are you correcting for that possibility? So an easy way to do this is to use bootstrapped standard errors. So do some bootstrapping. Pick yourself up by your bootstraps, right? And that's what we do here. And thankfully, you're able to do this in Mplus. So I can just go under the analysis command and add bootstrapping. So this is going to bootstrap my standard errors. I think this is bootstrap. And I pick some value. Now, it takes a while to run these, so I'm just going to do, just to show you, I'm going to do like 100. This might be too many for a quick demo, right? So it takes a while to run each of these. I mean, normally you'd want to do like several thousand, maybe 5,000 or something like that, even 10,000, but you'll see that it's not a quick run. And because I'm doing a video, I'm just going to show you what this is like. So we're going to compute these standard errors using bootstrapping, and you'll see that it's not very fast. Because of that, again, like I said, so you see, like, I'm doing 100 of these runs. If I did like 10,000, I would be here for a long time. So it's going to run these for me. So basically, it's going to do a sampling distribution based on this new population, right? Based on what the population of our data are, right? And the results that we have, right? So it's creating its own population, and it's going to sample 100 times from that population. So we're basically creating our own sampling distribution and using that to compute our standard error. So we get more accurate standard errors. And again, this is only 100, so this wouldn't fly if I try to submit something for publication. I just did 100 Busan, and I think at least 1,000 or 5,000 or 10,000. But what I'm going to do is I'm going to look at these values again with the bootstrap standard errors. And in my experience, they're much more stringent, right? And again, here, because I only did 100, you see these are still significant. I don't know what would happen if I did it with 1,000 or 5,000 or 10,000, but that's what you want to do, right? Because the raw or crude standard errors are not good enough. Okay, so this is an example of how you would run a mediation analysis. Makes a lot of sense because, first of all, it was an example of how we did an associated processes model. So that's a model in which we have two processes running side by side, right? Basically, right? So why we do that, and you could also do something else. You could also do time varying covariates if you prefer. So that's where time varying covariates are. So covariates are things that we control for, right? And we can do, generally people do covariates at baseline. Like you take something like gender, and which doesn't change, but you take it at baseline and you look at its effects on the intercept and the trend. However, sometimes you have things that change over time. So in this case, we were looking at two things that change together, right? We thought would change together, right? So that's the reasons for vaping and then actually vaping behavior. So we used the latent variables to test how they're related. You could alternatively do variable to variable at the same time point, like does reasons at time point 1 affect reasons at time point 2? Does reasons at time point 1 affect vaping at time point 2, and do these crosses and stuff like that? Or you can do all that stuff too. Yeah, cross lag type model. You can do all kinds of stuff, and we can do that in the latent variable framework too. I can check whether there's an effect from one to the other. So it depends on what you want to do, right? But this is a common thing that'll occur is you look for mediation, because things, when you see these models, you say, okay, the effect of smoking might not be direct. It could be actually indirect through one of the reasons variables. Okay. So this gives you some idea of how to do that. So I have one more that I want to show you that's kind of cool here. All right. And this is, two-part model. Actually, I published a paper. I think I used this, yeah, to show how we do analyses when we're counting something, right? When we're counting something like days of use of e-cigarettes. And I did a paper in which I compared it to the use of area under the curve as an alternative. But this is a two-part model. So when you have data that are like counts, right? Like you're counting the days of electronic cigarette use in the last year or last 30 days or something like that. What you're going to have is you're going to have two things, two components of that, right? You're going to have a use versus not using, and then you're going to have numbers among people who do vape, right? If I just looked at the data for, say, 1,000 people, the majority of people are not going to vape. So what I'm going to do is and I ask, how many days did you vape in the last 30 days? The majority of people are going to have zero, right? So you get this inflation of zeros, right? These are count data, and count data follow what's known as a Poisson distribution, right? So it's count, right? How many times something occurs in a given period of some sort. So that's what you have. You have this Poisson distribution. However, when you're dealing with substance uses or these more rare events, you're going to have an inflation of zeros because most people don't use. So you can model this using a Poisson, and you can do that in a lot of different ways. You can do that with generalized estimating equations and other types of methods, including growth curve modeling, but depends. It doesn't always work out that well with the data that I have. I mean, I haven't had as much luck using it as a Poisson process. But an alternative is to split the data into two, have a binary component for those who use versus don't use. So this is really cool because now I can predict what factors actually, I can actually estimate what factors predict use versus no using. And then among those who use, what factors predict change. Okay, so that's basically what this type of modeling does. So we call it a two-part model, right? So these are data two-part. So these are actually, this is what you have to do in there, right? So this is my data set. Again, I had to split it in two because it was too long. So this is just where the location of the data set. It's another CSV data set, comma separated variables. It's a two-part model. So I name my variables, right? There are these e-cig variables. And then I divide them into a binary part and a continuous part. That's pretty cool, right? The binary part I call, well, very cleverly bin1 through bin6, and then continuous variable continue cont1 to cont6. Okay. And then I have all my other variables that I'm using in there. Okay, they're just listed. The user variables in this case, so I'm simplifying this just for us in this example. I'm only have one predictor variable. It's going to be smoking. And then we have the binary part and the continuous part, where the categorical variables here are the binary part. Obviously, the continuous are not. Okay. I have a robust estimator here. Well, one reason for that is that my continuous variables are not necessarily normally distributed, and because they're not normally distributed, they're going to be well, we have to deal with that, right? So we take a natural log transformation. So it's just something that's inherent in the process. There's a natural log transformation for these variables, and then we use robust estimation for the parameters. And then we set what our missing data are. And in this case, I made smoking a binary variable, like yes and no. Oh, and then the covariance coverage has to be, so this is one, so there's a certain limit to how much data you have to have at each time point in order for this to occur, right? And what I'm doing here, I'm saying, hey, we can allow for the use of data even when there's very, very little data. So it looks at how many data points there are at each of these times. So the correlation about with the completeness of the data at all the different time points. So I said, well, we can do this, make it really, really small just to make sure this model runs, right? Because I might have very few data points at some of these time points here. So I modeled two parts, and just out of convention, um, we call the binary variables U variables, and then the continuous variables Y variables, kind of like convention. So I call this my intercept variables I electronic cigarette U because it's the binary. I let the U represent the binary, and then this is the growth factor. S stands for slope. That's in my vernacular. I stands for intercept and S stands for slope. So that's why I always do I and S. That's kind of funny, I and S, right? And then here I do Y variables for my continuous component. So I divided everything into this is so great because now I don't have to worry. Okay, well, we know we have this zero inflated Poisson variable, right? With a predominant number of zeros because there's substance use. So I know I have that issue. So let's go ahead and deal with that, right? But by creating this model that includes a binary part and a continuous part. And then I set these variances to zero because this model is actually tough to get to fit sometimes. And this is kind of something I've done by convention is to set, and again, this isn't going to impact the model in really any negative way, right? So set the variances, the residual variances to zero, or the variances. Well, they're going to be residual because like they're have things predicting them. Set those to zero, their variances. And then I go ahead, in this case, I'm going to predict all of the latent variables on cigarette smoking. All right. So we'd expect that you'd have a positive relation with initiation of use. So this did not use to use, and maybe with use over time, the continuous component, because people may switch from cigarette smoking to vaping, right? And also, in this case, I also introduce something else here. I do a plot, type plot 3. So this allows me to see what the variable looks like over time. Like I'm going to get them look at the mean levels to see are they linear? Maybe I should change that. And I ask for a whole bunch of different types of outputs here, including standardized values, just so I can take a look at this model and do a nice analysis once I run it. So let's go ahead and run. So you can see it has to do a little work in there to do estimation. I love watching that work. And it's nice when it works quickly. Having a good higher power computer helps, right? So this button here allows me to go to the figure. So what do I want to see? Like histograms, scatter means, estimated means, medians, percentiles, sample and estimated means. So this, I think this is what I want. Sample and estimated mean. I think that's the one I want. Let's take a look. There you go. So it shows me the estimated means. So linear, this C doesn't look very linear, right? I don't even know what that is. More than Q, it has a bunch of turns. But when something gets has that many turns to it, I think a linear model is a better way to represent it. Because you can overfit something, right? You can say, oh, I'm going to square this, cube this, take the fourth. It's interesting because one of the things I'm working on in terms of area under the curve is its use when you have more complicated models like that, and you're not interested necessarily in the rate of change. You just want to know what the overall, value is. So that's where I use area under the curve. And just like I would do the area under the curve here, right? But one of the things I was doing is I calculated using this one equation, trapezoid rule equation. But you can also do this by integrating underneath here. And one of the things I've been doing is saying, oh, well, what happens when we have like a ton of data? Like, what if we have, because now you have continuous data. Like, I'm wearing a Fitbit and my Fitbit's feeding me data constantly. Well, I don't care what the shape of the growth is when it's fitting me data every second because I'm going to have a lot of fluctuations. Just get the area under the curve. But what's the best way to calculate area under the curve? Do we do this like, the difference here and then add it to the difference here and here? I mean, that's a lot of work. Or do we do it by finding the equation, the best fitting equation, and then integrating? So I've been working on that. I haven't really, I think that just doing the trapezoid rule seems to work really well. And especially with the high speed computers now, it's pretty easy to do that. That's just been my experience. I've been looking at data, say on weight, that might make my weight every day, and I see all these fluctuations. And then I ask for the model, right, the best fitting model. So I use Excel for that. I get the best fitting model. Then using that model, I integrate, get the integral from whatever between whatever time points I'm looking for, and I get the area under the curve and compare it to the area under the curve using the trapezoid rule. And I haven't seen any advantage yet. And in fact, it's kind of, trying to find the best fitting equation to one of these graphs is not that easy. So in Excel, it's interesting. It allows you to do it up to, I think, six, the power of six. So you'll get a value and then you get an R square for that. So I can kind of get what's the best fitting model. And it's something that's easier to do. That's why I'm always looking for stuff that's easier to do, right? So that people who use the program, who use the technique can find it easily. So that's something I'm working on. So this model, I mean, I could say, okay, well, let's fit it, really closely fit it. What's this actual thing look like? But would I get much more information in this case than a line? Because really, if you look at it, it's kind of linear, right? I mean, it just has some minor fluctuations up and down. Is it really going to change that much if I go from a linear to whatever this is? That's a good question because simplicity is the key here. So this is a linear model. Okay. This is showing growth among those who vape. Okay. It's not showing anything about the binary variable, right? Not vape versus vape. Okay. All right, but it's interesting that you get a lot of good stuff here. So this is something that I like about Mplus is that the programmers, I don't know if it's Linda Muthane, who's the key head. I know she's one who, together with her husband, Bengt Muthane, created this program. And I think that they did a great job. Great job. All right. So we look at our results here. So a lot of stuff, right? This is the coverage, right? Proportion coverage, covariance coverage. This is telling us how much data I have. So you can see there in some cases it was 0.021, 0.009. So that's why I had to reduce the allowable data to a covariance coverage. I did it so small, 0.001, to account for these. Like for instance, this is saying that between the continuous variable at time point 6 and continuous variable at time point 2, there's only, this much data available, right? So it's not that much, right? So I had to reduce my coverage in order to capture it all. There's little things you have to go through. So this shows us progression in use. So this is not using versus using, right? So it looks like overall it increased over time, like 12 by whatever the time point 6. So this would be freshman year in high school, fall, spring, fall, spring, fall. So this is the end of the junior year, right? End of the junior year, you've got to 12%. And this is back in somewhere in the mid 50, I don't know, whatever, 2015 or something like that, maybe even earlier. I can't remember exactly when the day when we collected these. I'm not getting those usual fit statistics. However, I can use all this information to compare models. So you can compare models with Bayesian information criterion. You can take the likelihood, use a -2 log likelihood for models that are nested when one model is nested within the other. So you have stuff that you can use here, but I'm not getting those other fit indices. Okay, so that's important. These ones like the BIC, that's a really popular one to use, especially when we do things like mixture models, which I'll talk about next week, growth mixture modeling, etc. When you use those, you use the BIC to compare models. It's a popular way to compare. All right, so let's take a look at what our results are here. So here we're looking at the effect of smoking on whether or not one initiated vaping. So you can see from here, so smoking would be, we did a binary variable, 0 is not and 1 is yes. And I can't remember if this was past 30-day smoking or ever. I think this might have been past 30-day smoking. So this is positive effect. It's statistically significant. This is telling me that there, and these are all Z values. These are Z tests, right? We can, um, so they're based on a normal distribution of these variables. And that's okay because we have large sample size and we know the central limit theorem kind of, there's a convergence towards normality of distributions when sample size is large enough after a transformation. And so these are transformed values, right, to use the Z-test. So here we have a significant effect of of um of cigarette smoking on vaping at baseline. Okay. And again, these, if you recall, the latent variable is continuous. So, we can't really do much more than that, but it is significant. And then we also have a significant but negative effect of baseline smoking on initiation trend. And again, this is most likely due to a lot of people, the effect of baseline cigarette smoking on baseline vaping being so high. So there's probably just some decline. Or you could say there's a decrease in the rate of change over time. There's just not that much room to improve. And then in terms of the use among those who do use, this is the continuous part, right? Again, this is the binary part. This is the continuous part. We see that baseline cigarette smoking was related to the number of times a person vapes, right? And it's positive. This one, in terms of the trend, was not significant. Okay. And then there's so there's a positive correlation between the baseline levels of, well, it doesn't really mean anything between, and I started using it, so therefore I'm going to use it, right? So that's all that's really saying. Okay, so yeah, so and then you get your standardized values depending which type you want to do, whether it's just standardized, which variable it's standardized on. Usually I use it where it's standardized on both the X and the Y, the predictor and outcome variables. And these are what you'd use if I was making a figure. Okay. All right. So what's the bottom line here? So, hi, Sophia. What's the bottom line here? The bottom line is we today what we did, and I'm
Okay.
recording this, so don't worry, okay?
Okay.
What's the bottom line here? The bottom line is, and next week I'm going to move to something totally different. But the bottom line is we have latent growth curve modeling, which is an extension of general structural equation modeling. If you think about structural equation modeling, it started with what? It started with looking at paths among variables. Doesn't matter whether they were at the same time point or not, but it just looked at paths among different variables and it estimated the paths. Then it went from just doing observed variables to using latent variables, right? So we did things like confirmatory factor analysis, and then we did these models that say, hey, does depression impact something like, I don't know, obesity or something like that, or does obesity impact anxiety, et cetera? We did that in a cross-sectional sense using structural equation modeling. And we took what we knew about latent variables and used those to our advantage to model growth over time. And that's what latent growth curve modeling does, right? It models growth over time and it uses repeated measures of some variable. So like if I want to know what's the effect of time on use of something like e-cigarettes, and that's what we did in this particular example. Let's see what was the other examples I used. So like I did this one here, just vaping over time, just vaping by itself. You could see that we can model what occurs over time using latent variables. Like in this case, we used an intercept. So again, like a line has an intercept and a slope, but we used an intercept, a linear trend, and then even added a quadratic trend to try to model e-cigarette use over time, right? So that it's much more powerful. And what we're doing here is we're actually modeling each individual's trajectory, right, over time, and then we're taking the average trajectories for everybody, and we're using that as our outcome variable. So we can do things like say, hey, what's the effect of cigarette smoking on e-cigarette use at baseline versus rate of change over time? And I can add a whole bunch of variables. Then I showed you also that we can do what are known as parallel processes or associated processes models, right? I showed you the associated processes models where like here, I showed you associated processes models where we looked at two things occurring simultaneously. We looked at electronic cigarette use and then reasons why people choose to vape. And we looked at how they change together over time, right? Like here, we had e-cigarettes at time 1 through time 7, and then reasons for vaping from time 1 to time 7. And we were able to model, what's the impact of baseline reasons for vaping on rate of change in vaping over time and so on, right? And then we were able to add predictor variables to that too, like all these different predictor variables I used that, you control for some of them, but you also want to see, estimate some of their effects. And what we did, we also looked at indirect effects, and that was the cool part. We were able to model the effect of baseline smoking on electronic cigarette rate of change over time indirectly through the effects of reasons for vaping. And that was kind of cool, right? And I talked about why we can't just rely on the simple indirect effects and why we need to use bootstrapping in order to get bootstrap standard errors, like we did when we talked about this before when we discussed mediation and we used the process macro. So I don't have to use the process macro here because Mplus has a built-in ability to provide bootstrap standard errors. So I showed you that, and they're generally a little bit more stringent. So if you're ever doing one of these and you're like, wow, I got a significant effect, and then you do the bootstrapping, and it's not significant. It's kind of a bummer, but that's what you have to do. That's what we have to guard against is these false positives and false negative effects. And then finally, we did like I said, we did the two-part model, right? And that was the one where whenever we deal with an overinflation of zeros, which comes with any substance use. Like, hey, how many times have you done heroin in the last month? If I took 100,000 people, vast majority of them would say I didn't use heroin at all, right? So you get a lot of zeros, but then you'd have people who do use, and when to model those, that follows what's called a zero inflated Poisson distribution. It follows a Poisson distribution, a count distribution with an inflation of zeros. And to deal with that, what we'll do often, you can either model with a Poisson process, but it doesn't always work out that well. Sometimes it's easier to model, like we did here, a two-part model where we divided the distribution into the 0 versus 1, the never use versus use, to those who actually use. So then there's a binary component, and then there's a component that's continuous, okay? So that's what we did here, and that was really cool because that allowed us to test what's the impact of predictor variables on both initiation of use and then rate of change. Like, these are awesome techniques, and I know that a lot of people like them, and Mplus provides that flexibility. You can do some of this now with other programs. I know R has the ability to integrate some of this growth curve modeling, kind of like taking Mplus and building it into R. And then there's other, like when I first started learning about this, I used something called EQS. I don't even know if it exists anymore. And then there's other programs that allow for like Amos is one that's local here from Temple, I think. Amos, which is built into SPSS, and they also allow these. I think what made Mplus famous was the ability to do this with discrete variables, not just continuous variables. Now, I'm sure by now all the other programs can do it. I mean, SCM, structural equation modeling, is a really, really good tool to have in your tool belt. It's not an only thing. I mean, in my career, people started pigeonholing me. Oh, you're the guy who does a growth curve modeling SCM, and I didn't like that. At first, I thought it was cool, but now that I've been doing a lot of different stuff for a while, I kind of think, that's not a good thing. You don't want to be pigeonholed in something. You want to be flexible so you can do a ton of different things. So it's up to you though to build your own portfolio. But this taught me a lot. Like, for instance, the stuff I'm doing with area under the curve now resulted in some part from looking at growth curve models and looking at trends But it also came from other things that I do because I work with so many other people. Like working with cortisol, we learned that area under the curve is the way we tend to look at daily cortisol, right? So I mean, because cortisol changes, and usually when people measure cortisol, they do it 3 times per day, and it's like, which is the best? First time, the second time, third time, and the area under the curve turned out to be the wow, this is the best solution. So taking that, I said, okay, well, why not? Can we just apply to these? Because you saw the way these pictures look when we draw, they're lines, and the area under the curve is perfect way to integrate that information if you're not interested in the rate of change, right? Like if I'm interested in the rate of change, I'm going to go with growth curve modeling, right? Or maybe generalized estimating equations, because those provide me with more information. But if that's not of interest, and I just want to know overall what's going on, I mean, area under the curve is so much more efficient. It's just one variable, one mean, and one variance, right? So, I mean, that's so much easier. And it just depends on what you want to do. May or may not talk more about that before the semester ends, but so I'm going to stop. Hold on, Sophie. I'm going to stop the recording now. Thank you, everybody, for watching. Just stop this recording.